So for today, I'm going to cover the distributions and some basic statistical concepts such as central limit theorem and the law of large numbers. So these two theorems are the basis of many applications in data science and in statistics as well. It's really important to review the central limit theorem and law of large numbers. Okay, let's start with the distributions. The first and foremost, the normal distribution. This is one of the most important distribution that we take advantage along our career as a data scientist. So normal distribution, if someone asks you what is normal distribution, it's highly vague question, but it's really hard to answer at the same time because as you know, let me share my screen by the way. As you know, it's really hard to describe statistical or mathematical concepts in words. It's really hard to put them in words, but if this is the question, and if you are trying to, if you are going to answer this question in a short way, you can say that it's symmetric. Normal distribution has symmetric shape, like you see here. You see, consider that the mean value is 0. You have the same number of values on the left-hand side of the 0 and right-hand side of the 0. So the distribution is symmetric. This is the most distinctive feature of the normal distribution. Okay. Statistically speaking, normal distribution can be characterized by moments, the mean and standard deviation. These are called first two moments of the distribution. So normal distribution is a parametric distribution. What does it mean? So it's basically that if we know the mean and standard deviation, the variance, we can, we have the idea about the normal distribution once we know the mean and the variance of it, okay? Because we have the formula for the normal distribution. This is quite important because once you have the formula for a distribution, you understand the characteristics of the distribution. All you need to do is to find the mean and standard deviation, put it in there. You know the data, the X represents the data here. You know what the value is, you have the data at your disposal. So you just need to plug the data into this equation, put the mean and the variance and calculate the probability of the specific point. That's a huge information. That's a quite important information. Okay, so that's why researchers or practitioners try to take advantage of normal distribution. Even if they don't have normal distributed data, they try to modify it to have normal distributed data. So we have some techniques to modify non-normal distribution data into a normally distributed one. So it's highly common to apply these techniques to have normally distributed data. Again, it's really makes life easier to use normal distribution in our analysis. Okay, so mean, as you see here, mean determines the location. Sigma represents the standard deviation. Determines the shape. Okay, so if you change the mean, your distribution go right or left. If you change the standard deviation, the dispersion of the distribution changes. So let's talk about the sigma. Here, the blue line here, you see the blue line is 0.7. If we increase the sigma's standard deviation to 1.5, which is represented by green line, it is more dispersed. As you see here, it fluctuates around minus 3 and plus 3. Okay, so there are this is much dispersed compared to the 0.7. So this is the effect of sigma on the distribution, but it's still normal distribution. Do not confuse with that. We have still symmetric shape here. There are some questions, I guess. Rafael, sorry, we cannot share the notebook, but you can watch the video and take your notes. All right. So let's make some examples and try to generate our own normal distribution. We can do that using different libraries. For the sake of this practice, I will use SciPy and try to generate the probability density function. Sorry, I would like to talk more about probability density function before moving forward. So this equation right here is called probability density function because it gives an initial idea about the density of the data set. That's why it's called probability density function. Why it is probability? Because F represents the probability. The result of this equation gives us the probability of a specific point. You see X here? X is a specific point here. So we have the mean and standard deviation of X. So if we assign any value from X here, we generate the probability, not population, of course. Probability of this specific point based on the mean and standard deviation. And that's why it's really helpful to work with normal distribution. And again, I would like to highlight this fact. It's a parametric method because we have mean and we need to know mean and variance to derive the probability density function. Okay. All right. Let's move on to our example. I start importing the libraries first. Numpy as MP, import matplotlib, our main visualization tool. There's PLT, import mat. We are going to make use of it along the way from scipy.stats, import norm. I'm going to use this to derive the probability density function of a data, right? Import Seaborn. Seaborn is another library that we discussed in the previous session. If you do that, cnc.set, even if you use matplotlib, you use the background of Seaborn, which is more fancy, okay? So let's define the parameters. Mu represents the mean by convention. Sigma is equal to 7. It is standard deviation. X is equal to lin space. You know what the lin space is? Lin space generate equally and linearly divided numbers. It starts from, in this example, it starts from minus 30 and set 30. And I would like to have 100 samples. So we have, sorry about that. We will have 100 points between minus 30 plus 30, okay? Right, plt.plots. plt.plot. X, what's X is the lin space. I forgot to define the Y. Okay, Y is equal to norm.pdf. This PDF generates the probability density function, which is X, mu, and sigma. Let's talk about this. So as I said, this is the probability density function, the equation of the probability density function. What I do in this code is that I know the X, which is here, and I know the mu 0 and sigma 7. So what I do is basically substitute these values by this x, mu, and variance. Okay, that's all. Then I'm trying to plot this, and this is normal distribution. That's why I'm looking. I will have something symmetric. So PLT show. Let me run this first, and this one. Linspace, there's something wrong. It's MP linspace. I forgot to type MP. PLT plot, PLT show. Okay, there we go. What's wrong? What's unambiguous? X sigma mu sigma X linspace. All right, PLT show. It looks fine, I guess. Oh, I forgot X here. Okay. Here we go. So as you see here, the mean is 0. The many points gather around 0, and it is symmetric. So there's some question, I guess, from Emilio. When normalizing our data isn't an option. Normalizing data and normal distribution is two different stuff. Normalizing is a scaling method. Okay, when you normalize your data, you basically apply a formula like x minus x mean over x max minus x mean, something like that. So what you do is basically squeeze your variable, squeeze your data set so as to fluctuates between 0 and 1. Okay, so you scale it, and you put your variable inside 0 and in between 0 and 1. That's all. That's what you do when you normalize the data. Okay, but the normal distribution is completely different stuff. So why need to declare CNC set? Just to let you know, you don't need to have it. If you don't apply the CNC set, you don't have this grid and light blue line. Okay, if you do that, if you type this and this one, okay, it's default. Sorry, it's not default. As I run this, I will have the same plot in this Jupyter notebook because I did it once. That's why. If you don't have the CNC set, you will have the plain PLT plot figure here. The background will be white, not a blue one, the grid version of blue one. Okay, got it, thanks. When we normalize 0, 1 or minus 1, 1. It's 0, 1. It's 0, 1. It's 0, 1. Okay, so when you apply z-score or standardization, it's, you will have a 0 mean and 1 standard deviation, but your data, fluctuates over a wider range. Okay. All right. What else we got? So it's normal distribution, what the normal distribution looks like. So most of the time, normal distribution is defined by this standard deviation. So here you see the mu, which is mean. Mu is used to represent mean most of the time by convention. So if we go to the right, just by one standard deviation in a standard normal distribution, so it covers 34.1% of the data. Okay, so this part includes 34.1% of the data. If you move by 2 standard deviation, it covers like almost 48, almost 48% of the data. And if you do the same thing to the right, you almost cover 95% of the data. Okay, 95% of the distribution. You see, what is left is the left tail and right tail. Most of the time, the points beyond this, beyond 2 standard deviation is called outliers, or the excess point, or the anomalies, because they are these points right here may be huge. Okay, that's the reason. Okay, we don't have any question here, so let me continue with another example. I will use the histogram here. Let me import the pandas first. SPD. Okay, mu is equal to 0, sigma is equal to 1, and is number of observation that I have, it's 10,000. Okay, plt dot figure, I will try to introduce the size. 8.4 is fine. Okay, sample is my variable, and p dot random dot normal. So which means that I'm going to generate normal distribution, normal distributed data here, and assign a variable named sample. Okay, I will define the normal distribution here. Mean is mu, which is given here, which is 0. Sigma is 1. Sigma. You need to follow the order here, order of the parameters. Otherwise, you get you don't get an error, but you have something different. N is the number of observations. So I need to have at least 2 parameters, 3 parameters here: mean, standard deviation, and the number of observations. Okay. So based on these parameters, I will generate normally distributed data, and which is called sample here in this example. PLT histogram sample. I will have 50 beans. You can play with this number based on your choice. Show. All right. Here, what I have. So, as you pay attention here, the mu is 0 and sigma is 1, which is a special case of normal distribution, and it is called standard normal distribution. If I have normal distribution with a mean of 0 and standard deviation of 1, then it is called standard normal distribution. Okay, great. So I have standard normal distribution here. My mean is the average value is 0, and standard deviation is 1, and I have symmetric distribution here, right? Symmetric shape. All right. It's possible to have to include the density on this plot. So let's do that. Let's apply the PDF right here on top of this histogram. Okay. So let me do that. Mu sigma n is equal to, I will redefine my parameters here. You can define your own parameters. S is my new variable, normal distributed variable. Okay, mp random dot normal mu sigma and n. So my mean, standard deviation, and the number of observations, which are defined here beforehand. PLT dot figure. Figure size is again 8 and 4. I will draw the histogram, which is S. The S is the variable that I generate here. The 50 is the beans, and if I type density, I will show you what's the benefit of it. I will show it to you. Let me check. Okay, let me define the parameters here. I will have 3 different output for the histogram. I'm gonna make use of some of them. That's why I need to define it. So counts is the frequency that I have on the x-axis, and beans, you know that, I just ignore it. So PLT plots, I'm trying to define the probability density function because I have the histogram, as you see here. I have this one, but I'm trying to get the probability density function on top of the histogram. Beans, comma 1 over sigma. I just simply apply the formula here, probability density formula of the normal distribution. I can use the built-in function, but it might be more helpful for you. np.py np.exponential minus, I will explain this, beans minus mu squared over 2 times sigma squared. Okay. Comma line width equal to 3 color, let's say y. Okay. So yellow. This is yellow color. Let me check the formula first. This formula comes from the probability density function of the normal distribution. You can check it. 1 over sigma times inside the square root 2 times pi. Pi is coming from numpy. And then e to the minus data minus mean squared over 2 times variance, sigma squared. Okay? There is something wrong, I guess. There is a error in parentheses. Now it is fixed. Okay, PLT show. I need to have the date. Here we go. Let me make it bigger for you. All right. So what I have is the normal distribution and the PDF, probability density function of the normal distribution on top of the histogram. Okay. There's a question, I guess. If the normal distribution is skewed right, does that mean 80% data is covered? No, it doesn't. It doesn't. We cannot automatically say that. We are going to discuss the skewed distribution, Farida. Please, keep your question there. I will try to revisit your question when we get there. Is MP random normal, MP rand n? Yeah, that's right, Emilio. That's the same thing. You can do that. Okay. All right. So this is how we can have histogram and probability density function in the same plot. It's, very informative. And I would like to briefly talk about the importance of normal distribution, because this is one of the questions that I get most. Why we need normal distribution, how we can apply normal distribution. These are the kind of questions that that I get a lot. So normal distribution is very important for data scientists. The reason is that it can be easily summarized by 2 statistical parameters, mean and standard deviation. So once you know the mean of the data and the standard deviation of it, so you know the probability of the point. That's a huge information, as I said. The area under curve is 1. This one. The area under the histogram is 1, which makes it easy to calculate the probability of a distribution. Okay. In many areas such as psychology, finance, math, data are closely distributed to normal. You can find normal distributed data in nature as well. So that's why it's the distribution that we come across a lot. So the formula is derived. We have a probability density function. That's why it's really helpful to apply this in our analysis. Uh, Many of the common indicators, such as z-score and statistical tests, such as t-test and ANOVA, are based on the assumption of normal distribution. This is one of the other reason why we apply normal distribution. Some of the methods, such as z-score, t-test, ANOVA, principal component analysis, these kind of tests, these kind of statistical analysis require normal distribution, which means that if you don't have normal distribution, you cannot apply these techniques. Okay. All right. So these are the reason why we need normal distribution, why we apply normal distribution. Okay. All right. What we have here, let me check it. This session is 2 hours. Okay. So we characterize the normal distribution. So the question now is, how do you understand that data follows normal distribution? So is it okay for you to say that, oh, okay, the data is distributed in a symmetric way? Does it sound scientific to you? I don't think so. It doesn't sound scientific to me as well, at least. So there are some statistical methods to check if data is normal distributed or not. So we can do it by visually using QQ plot, or we can run normal test. Okay. So in this part, I will talk about QQ plots. Okay. QQ plots, which is known as quantile plots, helps us to understand if the data, if any data, follows normal distribution. Actually, QQ plus can be generalized to any other distributions. Like you can check if QQ plots fits to Poisson distribution, or a data fits, uniform distribution, binomial distribution, any kind of distribution. So you can check it using QQ plots. That's why it's quite helpful. So how we use it? In order to use QQ plot, we need to apply some pre-processing. So once we have the data, we need to sort it, because we need to quantile of the data. So it's quantile plot. That's why we need to percentile of the data. Okay. So QQ plots works like this. We put the benchmark distribution on the x-axis and the data that we have on the y-axis. The benchmark distribution can be, as I said, normal distribution, binomial, any kind of distribution of your choice. Okay. Here in this example, I'm going to use normal distribution on the x-axis and my data on the y-axis. And if the data follows the 45-degree line, then I can say that, okay, the data that I have follows normal distribution, or follows what the benchmark distribution is. Okay. If there is a deviation from the 45-degree line, so I can say that, okay, my data doesn't follow normal distribution. All right. So let's check how we can conduct the QQ plot by hand first, and then I will show you how can we do it using built-in package of Python. All right, so I'm going to generate a sample data. This is a data that I just, make it up. I'm using run date function, which generates random integer between 1 and, sorry, 10 size, size, have the size 1 to 50. Okay, let me show what this data looks like. So the upper bound is 10, as you see here, and I will generate 50 numbers. All of them are integer because I generate integer random integers, okay, using the Numpy package, Numpy library. So normally distributed data that I can do it by using NP random normal, as you know it. We use it before, random.normal. So you know this function. I'm going to generate normal distribution. I will define the mean using this, and I will define the standard deviation using sample data 1 again, and I generate same number of observations. I need to have it in order to run the QQ plot. Okay, let me run this, run distributed data. Let's say data. Normal distributed data, NP random normal, NP mean, samples data set 1, NP STD sample. Okay, I define the mean, I define the standard deviation, and number of observation. I'm all set. What is left is to sort the sample data set 1, sample data set 1, sort. If I do that, I sort it. Let me continue. I will draw the graph. In order to do that, I identify the figure size, 8.5, let's say, PLT figure. PLT.scatter. I will use scatter plot here. Normal distributed data is my x-axis, as I said before, because this is kind of QQ plot. That's why the benchmark distribution will be on the x-axis and my data will be on the y-axis. Sample data set _1. So this is my sample data that I generate from random integers. This is my scatter plot. As we discussed, in order to have the QQ plot, I need to have 45-degree line. So now I will have this 45-degree line for you. PLT plot. Okay. Inside the list, I declared list here inside the brackets. NP.mean normal distributed data. I basically calculate the minimum value of the normal distributed data, maximum value of normal distributed data, because these are the lower bound and the upper bound of the point of the 45-degree line. Then the same thing here, I just copied this whole part and paste it here. But what I do, let me try to do that. Okay, it's more traceable. Sample data set 1 here, sample data set 1 here. So I'm going to calculate the mean of the sample data set 1 and maximum value of sample data set 1. And I need to define, I would like to define the color of the plots. It seems like I'm ready to run this. Let me check it before running the code. I first sort it, okay, in a ascending order. I define the figure size, declare the scatter plot here, normal distribution data on the x-axis, sample data set 1 on the y-axis. I draw the plot, which is for 45-degree line. It has nothing to do with the data set, the distribution of the data set. It's just the 45-degree line based on this statistic, based on this specific values. Okay, I'm all set, I guess. Sample data set one. Oh, I forgot to sort the normal distributed data. If you don't sort the data, it's something like that. You see, it doesn't give you an idea. Here, it tells you that there's a huge deviation from the 45-degree line. So, which means that our data, let me label the data first to prevent any confusion. PLT X label sample data. Okay. PLT Y label is the normal distributed data. Normally distributed data, right? Sorry, this is Y, this is X. There we go. So here I have the 45-degree line represented by red line here. On the y-axis, I have sample data. On the x-axis, I have normally distributed data. What I see is that there is a huge deviation from the 45-degree line, which implies that the sample data does not follow normal distribution. Okay, let's check it using the histogram. I will do it bigger I forgot to do that. What was the name of the data? Sample data set one. As you know, histogram gives us the idea about the distribution. Okay, so I don't have enough data sets, so it doesn't look well. So here you see the bar, doesn't tell me anything. So I just draw the histogram to check if the data really do not follow normal distribution, and it seems like it doesn't. So let me rerun this, and before sorting it, I sorted, that's why it doesn't tell us anything. So yeah, still, I need to delete this. Doesn't prevent, create some confusion. That's why. So QQ plot basically tells us that sample data doesn't follow normal distribution. So let's dig into more. I will introduce another data set. And check if the data is normal distributed or not. Again, but this time I will use built-in function of QQplot. I will do that here, okay? From SciPy import stats. Stats in SciPy include some useful tools. You will see that the QQplot is coming from stats as well. And what else? Let me declare the figure size here again. Fig size is 10.4. Okay, PLT figure fig size 10.4. Number of sample is, in this case, let's say 100. I will define a variable named res stats.prop plot. Prop plot is designed for QQplot. It's in the stats package in SciPy. I will take advantage of it to draw the QQplot in a nice and clean way. Sample data set. Let me define another data set before moving forward, because I'm not going to, I don't want to use the same data set. Sample data set 2, let's say. Sample data set 2 mp random mp.random.randit. Again, it's coming from generate from the integers. The lower bound is 120, is the upper bound is 150. Size is 50. Should be 50. Sorry, should be 100. Okay. All right, let me run this. Sample data set 2, as you see that I just use it as it is. I didn't sort it. Okay. What else we got? Prop plots. Sample data set 2. Test norm. So if you do that, if you define the distribution, it's your benchmark distribution. Okay. You can check the manual of the prop plot and you see that you have other options for distributions. But here, for the sake of this practice, I will use normal distribution as a benchmark method. Okay, I have this one. Let me label the plot. Y label is sample data. X label is, sorry, it's inside the code. Okay, X label is standard, sorry, normal distribution, not standard, normal distribution, normal distribution. What's left is the PLT show. So let me check it before running the code. I need to run this first, and then the rest should work. Okay, what's the problem here? Oh, I have, how many observation I have? Do not need to declare this, by the way, I didn't use it, but why I have all input array along the, okay, so sample data set 2 looks like this. You see this array here. If I do that, I get rid of one of the brackets that reduce the dimension. So I'm ready to use this like this. Okay, then I have this plot. It's a bit confusing, but it's good to know it. So let me do it again for you. Sample, if I generate random integers, I have this data set. So if I dot shape, here you see one and sorry, you have one dimensional case, but here you have two brackets. It doesn't recognize the plots. It's not recognized in a one-dimensional case if you have two brackets here. Okay, so that's why we have this trick here. So we get rid of one of them. So we are ready to draw the graph. You see? So it's really easy to apply QQ plot using prop plots. Okay. And what we see is that we have automatically generated 45-degree line represented by red line here. And the blue dots is the sample data that I generated from here by using this code. Okay. So what I see is the deviation from 45-degree line. So when I say deviation, it's a bit vague word. I know that, but right after this example, I will show you what a normal distributed data looks like when you draw the QQ plot. So it exactly follow the 45-degree line, and that's why this deviation means that the sample data doesn't follow normal distribution. Okay, so it's the result that we can generate using this QQ plot. So let me do the same example using the standard normal distribution on the y-axis. Okay, why I'm doing this is to show you what the normally distributed data looks like in QQ plot. Standard normal distribution. I will generate this. How can I do that? You know it. I'm just, using a Numpy random module and call normal, but this time my mu is 0 standard deviation is 1, I will have how many numbers? Doesn't matter. Let's say 1000. Doesn't matter. Okay. I have this one. So let me copy this and just, change the name of the variable. I don't need this 0. What else? The benchmark is normal distribution. I have standard normal distribution. So it should follow 45-degree line. Okay. Standard. You see? It exactly follows the 45-degree line. There may be some deviation in the, right-hand side and the left-hand side of the distribution. There may be deviation in the, outliers. That's fine. That can be tolerable. So, but the story is this: the standard normal distribution, that the data that I generated here follows 45-degree line, which means that this data follows normal distribution. Okay. All right. So what it's all about QQ plot. So it's, as you see, it's quite helpful. So I would like to show you one more trick in terms of visualization that maybe you can take advantage, because it's really good to play with the figures by using some vertical lines and to analyze it. I would like to show it to you. I will define figure size, PLT histogram, normal. I will define the normal distribution first. I will define a normally distributed data. Normal distribution. Sometimes having hard time to type this distribution. mp.random.normal 50, 300, and 1000. PLT histogram, I will take it and use this one. Okay. What else? Beans is 20. Color C is, sorry, right, PLT VLAN. So this code here, draw the vertical line on your existing plot, existing histogram. Okay. So you declare the location of the vertical line. I would like to draw a vertical line right from the mean. Okay. Starting from the mean on the x-axis, go all the way up. Let's do that. Normal distribution. So the mean of the normal distribution data coming from here is the location of the vertical line. I can define the color like B, and I can define the line style as you can do in drawing the line plot. Solid. If you do the solid line, you will have the solid line. You can declare the line width, which is 2 millimeters. Okay. So I will copy this one and draw another vertical line, but this time I will define the, I will change the location of the vertical line like this. MP, the mean of the normal distribution, plus 2 times MP STD normal distribution, which means that I will draw a vertical line from the point that is 2 standard deviation away from the mean. Okay, this is what this is for. And the and the line style will be dashed, so which makes it more visible. And the third vertical line will be in the left hand side of the mean. So it is two standard deviation away from the mean, and it is dashed. The color, I will change the color. No, I can keep it blue, blue, and blue one. Okay. What is left is the plt dot. Sorry. What's left is the plt dot show. Let's draw this. What's the problem is the, let me see, color. C is not declared here. Color. Okay. Here you see I have a solid vertical line right exactly from the mean, and I have the dashed line on the left hand side and right hand side, which locates two standard deviation away from the mean. Okay, so it looks fine. So you can analyze the normal distribution by this, or if you want to analyze the outliers, you can use this method too. Okay. All right. Do you have any questions? Let me check it first. You don't. Seems like you don't. Sometimes you write from the chat. The question from Schumann, the visual inspection of deviation from 45 degree is nice to inspect normally. Is there a numerical metric to give the same? Like sum of square deviation. Numerical, there is no design numerical metric, but you can create your own method to do that, but there is no built-in code for that, Schumann. The second thing about detecting if the data is normal distributed or not is the statistical method, statistical test. So we have different tests like Jack-Barra, normality test. These are designed to check if the data is normal distributed or not. And to me, this statistical test approach is more solid, more rigorous way to check if data is normal distributed or not compared to the histogram or QQ plot. But, you know, it's good to have this kind of technique at your disposal. Okay. So one of the participants asked about the skewness of the distribution, as far as I remember. So as we discussed, normal distribution has no skewness. So it's symmetric. That's why there's no skewness, which means that the mean, mode, and median of the data is the same if it is normal distributed. So let me rephrase it. If the data follows normal distribution, mean, mode, and the median should be the same because it's symmetric. We discussed the central tendency measures in the previous lecture, in the previous session. This measures gives us the information about the distribution. So if you have same values of mean, mode, median, you can say that the data follows normal distribution. So if it's not the case, we have skewness. Skewness defines by the anomalies or the outliers, okay? So this is positively skewed because we have the outliers on the right-hand side, on the positive side of the distribution, okay? That's why it's called positively skewed or right skewed. Please pay attention here because this is a bit confusing because when people see this figure, they easily say that it's left skewed because it looks like, you know, the points gather here and they think that it's left skewed, but it's not. It's other way around. So it's positively skewed or right skewed because the points gather on the right hand side, the outliers gather on the right hand side, and skewness defines based on it. Okay, so negative skewness. Negative skewness, on the other hand, is define again the outliers, and the outliers on the negative side, that's why it's either called left skewed or negatively skewed. Okay, so in normal distribution, again, skewness is 0. And if you have skewness, the first data set, the median is greater than mean. So because the repeated values gather around here, but your mean skewed to the left. So that's why median is greater than mean. And this is the completely other way around in the third data set. The mean is greater than median. Okay. All right. So what else here? So this is what it looks like if we have QQ plot. So normal distribution follows this line of path here. Here you see some deviations, but you can, overlook it because most of the data follows 45-degree line. So when it comes to positive skewness or negative skewness, there is a, wild deviation from the 45-degree line, which, implies that the data does not follow normal distribution. As we discussed, normal distribution is one of the most widely used distribution. That's why I spent so much time on it. But I don't want to spend too much time on these distributions. That doesn't mean that we are not going to use this distribution along the way, but it doesn't, as important as normal distribution. All right. So we can, divide the distribution into two, like normal and non-normal distribution. We talk about the normal distribution. Let's talk about the non-normal distributions. I will start with the Bernoulli distribution. So Bernoulli distribution is one of the most basic distribution in data science, and so in statistics, sorry. So you basically an event with two possible consequences. That's all, like tossing a coin, okay? Or pass or fail, something like that. You will have two possible outcomes in an event. So the as you can imagine, it's a discrete case. It's not a continuous, like the normal distribution. We have discrete data, and that's why the probability density function turns out to be a probability mass function. Okay, in discrete case, we use mass term instead of density. So probability mass function for Bernoulli distribution is this one. This represents, for instance, success. This is failure. So this is how it looks like. Again, it's a parametric distribution because we need to know the probability of a specific event before calculating the probability distribution of the related event. All right. So in order to derive the Bernoulli distribution, we use binomial built-in function because, as we discussed, binomial is just a generalized version of Bernoulli distribution. So let's try to Bernoulli distribution using binomial. Random dot binomial. Okay. 1.5 and 100. So this one is the distribution parameter. This is the probability, and this is the number of samples that we have. PLT histogram. The data is Bernoulli coming from here. PLT.show. So this is what it looks like. We have two outcomes. It's either 0 or 1, as you see here. 0 dominates 1 in this case. Not dominates, but we have a larger number of observation in 0 compared to 1. So this is Bernoulli distribution in a nutshell. Let me repeat it. We have two outcomes in an event, in just one event. So if we iterate this event, if we have repeated number of observations, we have the binomial distribution. So binomial distribution and Bernoulli distribution is, you know, related, two related distributions. Okay. So the binomial distributions, if I need to give an example about that, is tossing a coin like 10 times, okay? But in binomial distribution, we toss a coin just once, okay? So the difference between binomial and binomial distribution in terms of probability mass function is the combination here, okay? We have this probability mass function. This is the same with Bernoulli, but we have the combination here because we have repeated events. That's why. Okay. So for instance, if we draw, you know, what's that? Roll a die. How many times? 10 times, let's say. And if the probability of getting, you know, so let's toss a coin, and probability of getting head is this 0.4. Probability of getting head is 0.6. Okay, and if we have head 6 times, this is the if we are trying to calculate the getting head 4 times, let's say, here you see, this is the formula that we need to have. This is 4, and this is the corresponding probability. We need to have, we toss a coin 10 times. That's why if we have 4 here, we need to have 6 here. And the complementary, you know, this complements the probability here. This is our main focus, this one. And this is the number of combination that we have, all right? So it's really easy to derive the binomial distribution in Python. I will do the same thing, but this time I will use repeated events. So here, let me show it to you. Here I use 1, as you see here. Now in this case, I will use, let's say 20, okay? Because I do this experiment 20 times. Random dot binomial. 20.5, 100. So I do the experiment 20 different times. The probability of 0.5, I will do it 100 times. I will have 100 samples. All right, plt.histogram binomial, and all right, this is what I have. So it doesn't, you know, normal distributed, as you see that. This is binomially distributed. All right, so the main distinction between Bernoulli and binomial is the number of events, repeated events. If you toss a coin just once, then it's Bernoulli. If you toss a coin more than one, then it is binomial. All right. So let me continue with the uniform distribution. Uniform distribution is, again, it's very helpful in, you know, if you are working in a specific range and the number of, if the probability of this specific range is equal, then the normal distribution is your distribution, okay? So it's basically works with a specified range, like here in this case, it's 0 and 5. We are working within this range, and the number of the probability of the events are the same, equal in this predefined range. So the outside of the range, the probability is 0. So here, if we have, if you are working with 0 and 5, we have 0.2 probability for 1, 2, 3, 4, 5. Okay, equally weighted. So that's why the probability density of the uniform distribution is really easy, and it is this formula: 1 over b minus a. B is the upper bound of the range, a is the lower bound of the range. So the density function is calculated with this easy formula. Okay, so if you are working with this interval 0, 2, you just simply calculate the probability density function of the uniform distribution, like 1 over b minus a, which corresponds to 2 minus 0, equal to 0.5. Okay. All right. So let's generate a uniformly distributed data using Python here. Uniform data is equal to stats dot uniform. I didn't import the package. Let me import the package first from scipy dot stats import uniform. Okay, uniform data is equal to stats dot uniform dot rvs random numbers. It's how we generate random number in stats library. We need to use this function. Size is 10,000. Location is 0, and scale is 10. Okay. These are the parameters that we need to define to generate the normal distribution. All right. What else we got? Okay, we are all ready to do that. I will do the. Let me show the uniform data to you first. This is what it looks like. Okay. So I will draw the plot using the pandas library, pd data frame. I will turn it into the data frame to take advantage of the pandas visualization package, because it's in an array format. So I will turn the uniform data into a df data frame. I assign the name df to the variable. And if you are going to use pandas line plot, you need to type the data first, df.plot, instead of plt plot. You can use plt here in this case, but I would like to show it to you because we did some example about the plt plot, but we didn't use the pandas library in terms of visualization. That's why I would like to show it. So y label is called density, right? And plt.show, I guess. Okay, here I generate uniformly distributed data, then I turn it into a data frame. I draw the line plots, I assign a name on the y-axis only, and show it in type plt show. Density, there is something wrong, I guess it shouldn't be capital. All right. So this is what it looks like, what the normal uniform distribution looks like. So it's fluctuate between 0 and 10. As you see here, I define it here by hand. So the data, the uniform distributed data, have the same probability, and outside the range they have 0 probability. Okay. All right, let's draw the histogram of it. plt.histogram data. This is what it looks like. Okay. The observation changed slightly. The frequency of the observation changed slightly. If you increase the sample size, you will have more uniform distribution, but it takes some time because I increased the number like 1 million. Yes. It will take time, but most of the time you will have more uniform look. Let me see. Okay. While waiting for it, okay, here you see you have very similar lines. So it's asymptotically same distribution, same probability. Okay, if I draw the histogram here, all the data points gets the same probability. Okay, same probability of occurrence. All right, this is what the uniform distribution looks like. I would like to briefly talk about the how we generate random distribution using Numpy. So it's really easy, but you just need to know the parameters, okay? If you are going to use Numpy instead of stats package, which is a bit different from the Numpy package, as you see that, you can use stats package as well, but I prefer using Numpy. np.random is the same for all the distributions that we have, okay? np.random dot binomial. So this represents the number of events, and this is the size. This is the sample size. This is the probability of the event. Okay, this is the same thing for binomial, but we have number of occurrences more than one. That's why we define n here. Sorry, we define n here. This is again the probability. So in normal distribution, we know it. I'm sorry. The mean, standard deviation, and the size of the sample size. Okay. And in uniform distribution, we define the lower bound, upper bound, and the size, which is 1, 1. If you do that, you just have one scalar, just one number. Okay. So here in this example, you have 1000 observation with a specific mu and sigma. Here you will have a matrix like 100 rows and 10 columns. Okay, most of the time we use one-dimensional case, like you see here, it's 100 observation we have. This is multi-dimensional case. All right, how about the main statistical theories? So let's start with the central limit theorem. Central limit theorem is, it shows the distribution, it shows the importance of normal distribution, because irrespective of the distribution you have, as you increase the sample size, the mean of the sample size getting closer to the normal distribution. I know it's a bit confusing, but let me try to visit this theorem, and it will make more sense to you. So we have a sample, okay? We increase the sample size, and at each iteration, we take the mean of it, okay? Let's say we toss a coin like 20 times, okay? We store the mean of it. Then we toss a coin another 20 times, and we store the mean. And 40 times, we store the mean, and so on. If we do it over and over again, this means that we store from the samples getting closer to the normal distribution, irrespective of the distribution that we have at the beginning. So the tossing a coin doesn't follow normal distribution. We model this data with either Bernoulli or binomial, depending on the case you have. If you have repeated event, we use binomial distribution to fit the data, the tossing a coin case. That's why we start with the binomial distribution, but the stored means, we store the means, and the distribution of this means getting closer to the normal distribution as we increase the sample size. This is what central limit theorem is based on. So if it try to generate the central limit theorem using Python code, it will make more sense to you, I guess. Let's do that. I will generate the package first from numpy.random import random integer from scipy import stats. Okay. All right. Means is equal to, in a list, I will use list comprehension here. We discuss it in Python session. Run it. I try to calculate the mean of the run it. Let me generate it. 1, 7. The lower bound is 1. Upper bound is 7. It's 6 actually. 7 is not included. And I will do this 60 times. I will have 60 observations. Okay. Sorry, for I in range 1000. So what does it mean? I generate random integers from 1 to 6, which corresponds to rolling a dice, right? This is the case of rolling a dice because I have an observation between 1 and 6. 6 is included. I have the number of observations, 60 number of observations. I forgot a parenthesis here, 60 number of observations. And each time I take the mean of it and I do this operation 1000 times. Okay. All right. Histogram means show print. I will print later on. Okay. Let me run this first and then this one. You see, it's very similar to the normal distributions, almost symmetric. If we increase the sample, let me start with 10. This is what it looks like. Okay, let's try with 100. Doesn't look good. 1000, getting fine. How about 10,000? Okay. How about 100,000? Okay, it's very similar to normal distribution. How about 1 million? I will stop here. It's gonna take some time, but not that much. Let's wait for it. It's going to be more similar to normal distribution. This is what I expect. By the way, let me type the, okay, here we go. It's symmetric. Looks like symmetric. Okay. So it's what central limit theorem tells us. Irrespective of the distribution you have initially, the mean of the sample size getting closer to the normal distribution. Okay. So let's calculate the main statistics of this distribution. Stats.describe. This is the main statistics of the data. So it's min max. This is the mean. Sorry, this is the mean. This is the variance. This is the skewness. So you can understand it from here. The skewness is very close to 0, which means that our distribution is symmetric, which implies that it's normal distributed. Okay. So the mean is 3.49. So if I calculate what this means, it's a list, sorry. Yeah, it's a list. Okay. I can turn it into a data frame, calculate something with that. And if I calculate the if I type describe to have in a better format, so this is what I have here: mean, standard deviation, minimum, maximum numbers. Okay. What's the median of it? 3.5. So what's the mean? 3.49. Here you see. Last time we discussed that if we have the symmetric distribution, we discussed that we have mean, median, and mode. the same mean, median, and mode. So it's, you see, it's quite similar. So that's why we can say that this is kind of normal distribution. And this is what the central limit theorem tells us. Okay. How about law of large numbers? So law of large numbers is basically says that the sample size matters. Okay. If you increase the number of samples, you basically better represents the sample population. If our sample population bias, even if you build a very strong, very powerful model with a good tuning, it doesn't work because your sample doesn't represent your population. Okay. If you have sample size of, say, 20, you cannot run a model with this. Okay. Because sample size of 20 doesn't tells us the doesn't represent your population. So we need more and more sample size, okay, to represent the normal, to represent the population. All right. So the thing is, the larger the sample size, the better representative sample population. So here in this plot, what you see is, number of the count of rolling a dice, okay, rolling a dice. So as you increase the number of dice you rolled, you are getting closer to the population mean. Your sample mean in the first case is 6. You get 6 when you roll a dice in your first trial. If you do it over and over again, your sample mean getting closer to the population mean, but here in a slower pace in the 100 case. If you continue to do the exercises like 2000 or 100, you will have a flat line around the population mean. So let's make an example about that and see how the law of large number work in Python. So sample, I will generate an empty list. Sample means is, I define another empty list. I'm going to use it soon. I define a for loop like for number shots, okay, in range 2000 shots is equal to mp.random.randit. I know that I'm rolling a dice, that's why I have my upper bound is 6 and lower bound is 1. My size is 1 every time I roll a dice only once, and I do this, this trick. This trick I tell you before. I will append this trial into the sample variable, which is a list as I define here for running the for loop. Sample underscore means inside the parentheses mp.mean sample. So here I calculate the mean of the samples and I store it inside the sample means, which is another list I defined before the for loop again. All right, I need another cell to calculate the results. Let's run this. There is something wrong. Oh, what's apple? It's append, not apple. All right, I have another problem here. MP mean sample. List object is not callable. So there is something wrong, I guess. MP random randit low 1 high 7 size 1 0. Okay. This is shot. Sample dot append shot. Sample means, oh, I forgot the appended. Okay, here we go. It works. So let me type first of all the sample first and samples. This is it. So I roll a dice, I get 3 and 1 and 6 and 1 and 5 and so on. Okay, these are my observations when I roll a dice. What are the means of this? Let me calculate it. Sample, we calculated before actually. Sample underscore means first 10 observations. Okay. So here for the 10 observations, we have the mean is 3 because this is the first trial. I get 3. That's why the mean is 3. In the second trial, I get 1. The mean is 2 because 3 plus 1 over 2 is 2. And it's 3.3 and it is 2.75 and so on. But I get, after 10 trials, I get 2.9, which is far away from 3.5, which is the population mean of rolling a dice. Okay, let's continue to increase our observations. So let me delete this and calculate the sample means. So what is the last one? Is 3.49. You see, 3.49. This is the last observation, 3.49. All right. So if you do that, pyt.plot sample means, you see, you try to, your first observation is 3 and your first samples, moving around here, and as you increase your sample size, you are getting closer to the population mean, which is 3.5 in rolling a dice. Okay, so how many times I try this? 2,000 times. I have 2,000 iterations. So as I approach the 2,000 observations, so here you see I have the sample mean is very close to the population mean. So this is the story behind the law of large numbers. So again, if you increase the sample size, your sample mean getting closer to the population mean. That's all. All right. If you have any questions, we can discuss, because I'm done today. I covered the topics that I have today. Please, feel free to ask questions if you have any. All right. Seems like you don't have any question, right? Okay, one question from Emilio. Sure, Emilio, you can ask. Oh, sorry, Rafael asked a question. Can you show this example code again of using the PDF formula? Thanks. All right, sure, I can do that. Where is that? PDF formula. Right here. Not there, sorry. Oh. Here we go. This is the PDF formula. Okay. So, Emilio, do you have any question out of scope? Oh, could you please explain the curse of dimensionality in KNN? Curse of dimensionality is a common phenomena. It's it happens in KNN too, but curse of dimensionality is this: if you have more than one features, more than one variable, as you change the dimension, if you change the value of the variable, it exponentially grows because you have more than one features. That's why you need to change the entire, you need to adjust the entire data set. So that's why once you change a variable, it affects exponentially to your data set. Okay, that's what the curse of dimensionality is. If you are working with high dimensionality, changing one variable leads to huge change in your data set. Okay. Isn't this a generalization of binomial distribution where the mean would be 2000 times 1/6? Amrit, could you please rephrase your question? I didn't get it. Are you talking about the law of large number case, Amrit? If this is so, yes, it's a binomial distribution. It's a generalization of binomial distribution. Yeah. But law of large number has nothing to do with the specific distribution. It just basically tells us that sample distribution is getting closer to the normal distribution. Sorry, getting closer to the population mean, sample mean getting closer to the population mean as you increase the sample size. Okay. We have nothing to do with the distributions in law of large numbers. Okay. Do you have, I need to refresh the, okay. Okay, let's stop here. I will see you in the next week in our final session. We complete the 10-hour Python course next week. I will see you in the, 1 week later. Take care since then. Bye-bye.